So hi, as Yop said, my name so it's actually Ojas Parekh. I get Ojas all the time in New Mexico, so I'm used to it. I get all kinds of stuff, but yeah. And thanks everyone, for coming so late on a Friday. I appreciate it. So I'll just start by saying that my background is in theoretical computer science and discrete optimization. And these days I could kind of pretend to be a physicist, especially when there are no other physicists in the room. But I don't know in this crowd how it's going to go. So definitely call me on any kind of, unphysical things I'm claiming to be physical or stuff like that. So, all right. So actually, what I want to talk about is quantum max cut and its two local friends. So I'll tell you more about that. So this is, in general, what I've been interested in these days is quantum optimization, some of you in the audience. And the first question really is, what is quantum optimization? So there are four natural things that quantum optimization might mean. And, one way of kind of characterizing what we mean by this is just looking at what kind of problem we're trying to solve and what kind of algorithm we're using. And the nice thing is that all four of these cases actually make sense and have interesting kind of problems and algorithms. So, if you're classical, of course, this is what people have been doing forever and ever. But even things like classical algorithms for quantum problems, this is how we cope with things like local Hamiltonians and stuff. We have heuristics, mean field approaches, stuff like that. And then things like the quantum approximate optimization algorithm, which I just kind of call QAWA, is like people trying to use quantum algorithms for classical optimization. And then, we have things like adiabatic and other sorts of things for quantum algorithms for quantum problems. Although I feel, in terms of rigorous approximations, that last box is really underexplored. So just to make sure we're all on the same page, discrete optimization here, I just really mean kind of representing solutions of some feasible set by binary vectors, and then you typically have a weight function. So I think the audience is probably familiar with this, and examples. There are many examples of such problems, and typically you define them on graphs. So in this talk, we're really going to be talking about the edges of a graph, and these are kind of where our variables live. So where the story starts is with max cut. So max cut is a fundamental classical optimization problem. And, it's actually kind of driven the field of approximation algorithms and related fields based on kind of developments for max cut. So the goal here is just to, you're given a graph and you want to partition its vertices into two sets to kind of maximize the weight or number of edges crossing that set. And you can also look at it as a constraint satisfaction problem, where for each edge you have a clause, which is just like, the XOR of a Boolean assignment to the variables of the graph. And, of course, on the approximation algorithm side, the 0.878, semidefinite program-based approximation by Gomans and Williamson really kind of started a revolution, and it's a revolution in a story that's quite strange in the sense that kind of doing better than this 0.878 number, which is some trigonometric thing that comes from analyzing the expectation of the algorithm, is actually unique games hard to beat. And so it's kind of interesting that the semi-definite program gives kind of what we believe to be the right answer. But kind of more generally, people have been looking at max cut for a long time. And particularly in the discrete optimization community, people like to look at polyhedral characterizations of optimization problems. And even there, looking at the cut polytope has been very fruitful, in understanding how facets work for optimization problems and that sort of thing. And then, recently it's been quite useful in kind of proving lower bounds on the extension complexity of linear and semi-definite programs, work that Ronald was involved in. So max cut in general has kind of had its fingers in a lot of pots, and it's been sort of a model problem that's kind of a test bed in many ways. So the question really here is two local Hamiltonians, like, oh man, that sounds great. Why can't I have that, right? And so if we want to define some problem like this, that's going to be an analog, what might it look like? Okay, so I tend to give talks to mixed audiences, and so people with a physics background, this is no surprise, but to me, it's like, when I learned about this kind of connection, it's like, why didn't someone tell me this earlier? In some sense, nature is inherently solving discrete optimization problems. You have physical systems, they have a discrete number of energy levels, and nature is trying to put systems in low energy states. And even more concretely than that, I mean, if we think of these Hamiltonians, these local Hamiltonians, kind of diagonal in some fixed basis, then they correspond precisely to classical discrete optimization problems. And so, there's a natural framework tying together classical discrete optimization and local Hamiltonian problems, which you can think of as natural quantum discrete optimization problems. So, this is what really got me excited about quantum optimization. So this is just kind of expanding on the story, but the idea really is that if you haven't seen this before, which I'm guessing you have, it's just that you kind of take your Hamiltonian that has 2 to the n rows and columns associated with basis states, and for classical problems, you kind of just put their energy value of each solution along the diagonal. And then, now, of course, just finding a minimum or maximum energy eigenvector corresponds to solving your problem exactly. If it's diagonal, it's just going to be one of the basis states. So, so this Hamiltonian perspective is great, but of course, to cope with physicality, but also sort of complexity, we need efficient ways of specifying them. And so what we focus on are local Hamiltonian problems, where really you're kind of telling the algorithm what's going on each edge or sort of locally, and then from that you can infer kind of sort of what must happen globally. So okay, so that's sort of how we can think of quantum discrete optimization problems, at least one way. And then what is a quantum approximation algorithm? So for the purpose of this talk, how I think of the algorithm is that you're given a local Hamiltonian. So you're given, say in this case, a 2 local Hamiltonian, a term for each edge of your graph. So really it's just a graph, a weighted graph as input, because the problems we'll think about will have the same term on every edge. And then the output should be some state. And now, if it's a quantum algorithm, so if this algorithm is running on a quantum computer, you might actually prepare some state. And so that's great. But, what if you're a classical algorithm? So in that case, you should output the description of a state. And here, description of a state is kind of vague. I mean, this could be some polynomial size representation of a state. It could be a classical algorithm that can compute Pauli moments of a state. You give me any kind of Pauli polynomial, and I output like trace of rho times that polynomial for you. There could be others. So here I take description to mean kind of a very generic thing, and you'll see what we mean by description concretely for the algorithms that I'll be talking about. So an alpha approximation, we're going to be looking at maximizing energies. It's more convenient for this picture, kind of max cut, sort of an analog to that. So all I really mean by an approximation algorithm is it's got to run in polynomial time, either quantum polynomial time or classical polynomial time. And for any instance, you want to deliver an approximate solution that has value at least alpha times the optimal value. And, of course, this is sort of instance dependent, and this is really kind of a worst case thing. So, this is sort of different from how more conventional notions of kind of approximations or heuristics. So for theoretical computer scientists and their ilk, we look at worst case approximation almost, in some sense, because we have to. It's hard to prove things in other settings, but really, so the idea here is that we really just want worst case performance, and this is different from what you might do in practice. So, okay, so what's the physical motivation for quantum max cut, and what is quantum max cut? So really, quantum max cut, this is just I mean, I hate to say it, but it's kind of like marketing, right? Like quantum max cut is really just the Heisenberg model, and you kind of negate the sign and you throw in an identity term. I will. So Sev Garibian and I introduced the problem, and I'll totally own up to the fact that it is the quantum Heisenberg model. But there's a good reason for doing this. So oh, by the way, there's physical motivation for the Heisenberg model, and I understand some of the words in this motivation, and so if any of you can explain, so many of you kind of cross physics and computer science, theoretical computer science. So I'd love to learn more about what some of these things actually mean. So I'm totally open to kind of learning more about stuff that's in my own slides. So the idea here is that if you just had, can you all see my cursor, by the way? Or just the slides? Okay. So at the bottom left here is the antiferromagnetic Heisenberg model, if you're trying to find ground energy. So this is really well studied in condensed matter. And the idea here is that the way we've written quantum max cut, like I said, it's just the sign shift, just negating everything, throwing in an identity, and then maximizing instead. So if you actually want a true ground state, it's an equivalent problem. But from an approximation point of view, it's not, because you've added this identity term. Sort of the approximability of the problem changes. So for the Heisenberg model, in the worst case, we have log factor approximations, and those are probably the right answer. It's hard to prove kind of lower bounds, but log is probably the right answer for approximating quantum Heisenberg, in the general case. But when you look at quantum max cut, on the other hand, well, now constant factor approximations are possible because of the identity term. So this is, and it's not just that, but adding in the identity term really makes the problem nice. So it gives a sort of a great characterization of what's going on. So I'll explain it on the next slide. So before I do that,
just to be safe, can I ask a question? Yeah, just to be sure that the sum, it goes over edges of a graph or over all pairs?
It goes over edges of, edges of some fixed interaction graph.
Yeah, thanks.
And then I haven't included it, but all of these results apply to the weighted case too, where you could put non-negative weights on the edges. Thanks for asking that, by the way. Okay, so what happens when you throw in this identity term is actually each term in the Hamiltonian becomes the projector onto a singlet. And so now you could think of this problem as like, I have, projectors onto singlets on each edge of some interaction graph, and I want to find a state that's maximizing the overlap on each edge. And so it's a very natural kind of problem, and so, yeah, I mean, initially, the identity may have appeared. We may have done this transformation to make it look more like max cut, but it turns out that this was kind of the right thing to do because the singlet picture actually gives you a lot of structure. So, earlier I alluded to the fact that it'd be great to have sort of a model to local Hamiltonian problem where we can develop the theory of approximation algorithms. And max cut is sort of filling that role, So here's some nice things about it. It is QMA-hard. And as I mentioned, each term is maximally entangled, which is, kind of intuitively maybe the right kind of thing you'd want for a model quantum problem, but also it makes things kind of practically nice because, then you don't have any one local terms on edges and stuff like that. It's very clean. You only have two local terms on each edge, and they're kind of, they interact nicely. So there have been, because this is sort of a clean version of two local Hamiltonian, it's been amenable to approximations. So there have been some recent works on kind of approximating this problem, generalizing, classical discrete optimization techniques like semidefinite programming hierarchies and rounding stuff. And then there's also evidence of unique games hardness. I say evidence here because, we had a paper where we thought we showed unique games hardness for like a version of quantum max cut. It turned out there's a bug in like, this vector version of kind of Borel's inequality that we're trying to prove. And, this is like the technical details of the place where the bug appears were far beyond me. This is sort of this wasn't my specialty. This is like using kind of, calculus of variations to kind of argue things about optimal vector arrangements on sort of infinite graphs, things like that. But we still feel that the theorem's right and we're working to fix it. So the thing that we know that's unique games hard is there's some constant factor for which, getting a better than approximation is unique games hard. And that constant factor is 0.956. And where that comes from is actually that's the best, that's sort of, if you thought about approximating quantum max cut just using product states, so you could say, what's the best product state approximation to quantum max cut? So you're comparing yourself against the best energy achieved by some product state, and then you're trying to approximate using a product state. Well, it turns out there's a 0.956, ... approximation, actually using, it's just kind of rebranding an algorithm by Jaap and some of his collaborators. But we proved, we conjecture that beating that is actually unique games hard. So that's a tight unique games hardness result for the product state version of the problem. But, it also gives a hardness result for the general case, so finding energy better than 0.956 is probably unique games hard. And you could probably improve that considerably if you're not looking at the product state case. It's just that we don't have the tools to do it right now because it's going to relate to things like quantum PCP, so.
Sorry, may I interrupt for a question?
Yeah, sure.
So I would expect quantum max cut to be at least as hard as regular max cut, in which case the unique games hardness of regular max cut would carry over. What am I misunderstanding here?
Yeah, so it's not like a strict generalization, in some sense. So it's like the diagonal of quantum max cut is like a scaled version of the diagonal of max cut. So I'll talk about that on the next slide. But really, it's more like these problems have parallel stories. They have kind of analogous behavior, but they don't have a precise relationship.
Oh, I see. So they're strictly speaking incomparable problems.
Yes, yeah, they're incomparable problems. And in fact, the story does break down. There is some kind of quantum weirdness in the story for quantum max cut versus max cut. So I'll definitely talk about that too. Thanks, Ronald. And then the other thing I want to mention is that, okay, so in the case of classical approximations, max cut, like I said, is kind of driven approximation algorithms for all types of constraint satisfaction problems. But technically speaking, if you want a statement like, give me a problem where an alpha approximation for this problem gives you an alpha approximation for any two constraint satisfaction problem. Well, that problem is not max cut, it's actually max and. So it's a classical problem known as max and. So like whatever approximation you get for max and, you get the same thing for any generic 2CSP. And so in the classical case, max cut and max and are kind of different problems, and they have slight differences in approximability. I'll show you in a few slides. But in the quantum case, something nice happens where quantum max cut kind of generalizes max cut, and you get some nice structure because of that. But it also kind of generalizes, or it also is sort of, what we conjecture to be the hardest instance of two local Hamiltonian where every term is positive. So in some sense, what we conjecture is that an alpha approximation for quantum max cut gives you an alpha approximation for any two local Hamiltonian problem with positive terms. And we have some results in that vein, and we know how to take algorithms for quantum max cut and systematically turn them into algorithms for positive two local Hamiltonian. It's just that the story breaks down a little bit because these things are harder to analyze numerically, and it's harder to come up with approximation factors. So, what really ends up happening is if you look at quantum max cut, so this is just each problem on a single edge. You can generalize this story when you take tensor products with identity and sum them together in the usual way. But what happens is that, if you have any classical 2CSP, then what you do to turn it into a local Hamiltonian problem is you just kind of put, that Boolean function on the diagonal of your local term. So the max cut term, the max cut Boolean function is just, you earn 1 when your 2 bits are different, so that's what we've got on the left. And quantum max cut is now a non-diagonal, operator on each edge. And if you look, the diagonal part is actually like max cut scaled by 2, right? Because the diagonal part is just I minus z I zj over 4. So sure, if you're just looking at like basis state solutions and stuff, you know, you can always sort of relate the two. But you know, more generally, if you want to earn maximum energy, you're going to have to do something quantum. And what's important to note here is that the best product state solution to quantum max cut, even on a single edge, only earns half the energy. So, you know, you could see that right away just from this Hamiltonian having diagonals terms of a half. So in some sense, you know, if you're using product states to approximate quantum max cut, you're a half is a natural barrier. And then you could also try and generalize constraint satisfactions more, you know, more generally than just quantum max cut to the quantum case. And one way to do that is just to think of your classical CSP and think of it as a diagonal rank K projector. And you know, if you have a rank 3 projector, you have like satisfiability where there are 3 ways to satisfy each clause. If you have this max and thing that I'm talking about, you know, it's a rank 1 projector, there's only 1 way to satisfy each clause. And then if you have like max cut, there are 2 ways to satisfy each clause. But in general, you know, you could just, instead of looking at diagonal projectors, you could just say, oh, let me define a local Hamiltonian problem by putting projectors on each edge or sums of projectors, and then, you know, constraining their rank. And for this, you have a similar story like for classical max sat, where random assignment, you know, classical random assignment gives you an immediate trivial approximation of K over 4, where K is the rank of the projector. You know, so like, for example, you get a 3/4 for max 2 sat, you know, et cetera. And the same thing for quantum versions of sat. So putting all of this together, this is kind of, you know, what's going on in quantum problems and then sort of related classical ones. So here I have 4 problem classes, and these have all, you know, they're classical versions that have kind of been well studied. So if you just look at sort of the most generic thing, or a generic 2 local Hamiltonian problem, this is one where you just sort of assume that Hij is traceless. You know, identity terms are only going to help your approximation factor. So just assume you don't have one and make no other assumptions on the terms other than they're 2 local. And in this case, the natural NP-hard classical problem is the max Ising problem. And, you know, both the quantum and classical problems enjoy 1 over log factor approximations. So the quantum 1 over log is by Bravi et al., you know, recently. And then the classical one is sort of a very nice algorithm by Cherker and Wirth. And so the Bravi et al. Result actually generalizes the classical result. You know, that's a common theme with all of these. And then we could look at max positive 2 local Hamiltonian, as I just mentioned. And you see in the classical case, you know, that one has a 0.874 approximation where max cut is 0.878. So it's slightly different. The algorithms are related, but slightly different. And then, you know, on the quantum side, we've been looking, Kevin Thompson and I have been looking at max positive 2 local Hamiltonian, and random assignment gets you a quarter, like I mentioned. You know, there were some results kind of working up to this 0.498 approximation. So I'll tell you where this 0.498 comes from and why it's interesting. But you know, 0.5 is the best possible approximation, and we actually were able to achieve this, which was kind of surprising. So I'll tell you more about this story too. So you know, but the problem with the positive 2 local Hamiltonian is that these approximation guarantees are all sort of, you know, if you believe that like nasty integrals converge kind of thing, you know, it's not like max cut where you have one parameter and you kind of optimize it to get the approximation ratio. In these problems, you'll have like many parameters and you have to optimize them, and the optimization problem, you know, becomes a little harder, much harder. And so, you know, I wouldn't necessarily call these kind of like rigorous results. They're more numerical results, but the story here is probably what's going on with them is the same as quantum max cut, which is the next row down. And there, the 0.498 approximation was the original one. And this actually corresponds to, you know, the integrality gap of level 1 of the Lasserre hierarchy. So if you take the natural SDP relaxation, it turns out 0.498 is kind of the best you're going to be able to do. And so, you know, that's with max cut, you get 0.878 from the first level, and that ends up being the best you can do up to unique games. So the fact that we could do better in polynomial time was kind of surprising. You know, we can actually get an optimal approximation of 0.5 for quantum max cut using product states. And then going beyond product states, we could do marginally better, but really, you know, we're kind of stuck in some sense. We don't really have good ansatz for approximating quantum max cut. And so I'll talk a little bit about that too, but you know, we need new ideas, right? So I'll leave it there, but you know, you could also look at quantum versions of 2SAT and other problems too. And you know, the only thing I want to say about all of this is that these are all approximations for unconstrained problems, for constraint satisfaction. You know, you could do the same kind of thing for constrained optimization problems. And classically, there are many, many, many of those that have been studied over the last, you know, 50, 60 years, like formally, rigorously in terms of approximations. And so when we think about quantum algorithms for those or quantum approximations for those, they're virtually unstudied. You know, Kevin and I have done some work on like quantum versions of vertex cover, but you know, so the point here is, I think there's a good analogy between classical and quantum approximation algorithms, but you know, in general, the quantum side is massively understudied. So for max cut, you all are probably familiar with the standard semi-definite programming relaxation, you know, that ends up being related to a vector program, where you're just kind of trying to take all the vertices of your graph and embed them on a sphere. And then you kind of, you know, take a random hyperplane to cut the sphere and decide which side each vertex should live on. So this gets the 0.878. Yeah, Jaap, did you have a?
Yeah, sorry. Could you go back one slide for a
Yeah,
second?
sure.
I'm just a little bit stuck by the second row.
Second row.
On the semi-definite case, can you help me there? I was expecting to see a number like pi over 2 or 2 over pi.
Oh, yeah. Excellent. Yeah. So that's right. So there is right. So there's this like Nesterov, you know, 2 over pi classical approximation when you assume that your objective function is basically positive. You know, I mean, this is one way of looking at it. And so the distinction here is that I'm talking about the case where each term is positive. And those approximations, the 2 over pi, apply to when the whole Hamiltonian is positive, not necessarily each term.
But that's different, right? So here's, I don't understand what, but then isn't it?
So
positive,
so,
then why is it non-trivial? So it's coordinate wise non-negative.
Yeah, so each term, each Hij is PSD. And so what you could prove here, you know, any approximation for what I have written on row 2 would give you an approximation for the case you're talking about, where only H is guaranteed to be PSD, but not each Hij.
Okay.
But it won't go in the other direction, and you'll get better approximations for that case. And you can I haven't mentioned here, but you can do that.
Okay, thanks.
So okay, so that's the standard max cut relaxation. And how do we get, you know, relaxations for these quantum problems? So this, you know, systematically, this comes from the quantum Lasserre or quantum sum of squares hierarchy. But, you know, there's kind of an easy way to motivate this, which is just assume that you had a state psi, you know, a true quantum state. And so let's define a PSD matrix from this psi. So the first thing I'm going to do is I'm going to define this matrix V, where I'm just kind of, you know, applying psi to each poly term. And here I've done it to the one local terms, but you could do this to any poly term. So then you've got this matrix V, and then if you look at V dagger, that's guaranteed to be PSD. And what V dagger is giving you, so in the upper right, you know, you could look at each block, and it's really giving you the moments of your state. So in other words, you know, if I have a matrix where I label the rows and columns by poly terms, And each entry of the matrix is the moment that you get by multiplying the poly term on the row by the poly term on the column, then that matrix has to be PSD. And so that's the basis of all of these relaxations, So this is true for any quantum state. So of course we could just kind of we could construct this PSD matrix and put the appropriate constraints on it and insist that it's PSD, and that would be a relaxation. The one thing to mention here is that this is going to be a complex matrix in general, but for all of these approximation algorithms, it turns out that just looking at the real part is enough. So you could just look at, for example, the moment matrix plus its transpose, which is also guaranteed to be PSD, and we'll get rid of all the imaginary terms. So this perspective, what it ends up giving you is that for the case of quantum max cut, the only constraints you really get are on the diagonals. So on the diagonals, you would have had the one local moments. And if you look at the complex version, you would have had things like the moment for X and the moment for Y is I times the moment for Z. But, when we look at the real version, all those imaginary things go to 0. And so you get this very nice kind of relaxation where you just have each diagonal block is identity. And so at the bottom, I've written the corresponding vector programs. So if you look at the vector relaxation you get, what you want to do is for each vertex in your graph, you have 3 vectors. So these are, for each of the poly directions, the poly axes, X, Y, and Z. And then they need to be unit vectors, and they need to be mutually orthogonal on each qubit. And that's it. This gives you an upper bound on quantum max cut. The kind of interesting thing, what ends up happening actually, is that this ends up being almost exactly the same relaxation as you get for max cut. So, you could look at this a little bit and realize that you could turn this into a relaxation that looks like max cut just by, kind of the relationships I've outlined on that blue arrow. But what you end up getting is you get the same constraints, but only the objective differs. So it's kind of interesting that, for both problems, the classical and the quantum, you have the same constraints, but only the objective function differs. And so, you would think that the stories would be kind of parallel, in the sense that, well, if for max cut, I'm getting a 0.878 approximation using this relaxation and it's unique games hard to do better, maybe that's also what happens for quantum max cut. So for quantum max cut, using this relaxation, you get 0.498. And your first instinct, which was ours, was that, oh, okay, yeah, 0.498 is just an artifact of the fact that, it's NP hard to find the best product state, and, going higher in the hierarchy isn't really going to beat 0.498. Classically, it doesn't help to look at stronger relaxations. It doesn't improve the 0.878. Okay, so maybe that's exactly what's going on here. And so we thought that for a long time, and then we realized you could actually get a 0.5 approximation. So even though it's NP hard to find the best product state, we can get the best product state approximation. So it's a little weird. So in some sense, in the quantum version, this relaxation is an optimal. Going to a stronger relaxation actually gives you a better approximation, but that's not the case for a regular max cut. So what do I mean by better relaxations? Well, as I alluded to earlier, you could kind of include higher degree polynomials to get bigger and bigger sort of relaxations. And it turns out, where all the action is kind of in the second level, where you're including 2 local poly terms. And so this is what Kevin Thompson and I have been studying. And it turns out, this is enough to give you kind of the optimal approximation with respect to product states, and also reasonable approximations more generally. I really, I wouldn't be surprised if the second level gives you the best possible approximation. We have no clue what the story is for quantum max cut. It could be, so classical max cut, the first level gives you the best approximation. This is what's conjectured to happen. With quantum, it could be that it's some constant level, that gives you the best, or it could be that these things, progressively get better. It's just the intuition is very different. And so it's kind of interesting to understand what's going on with all of this. So, the 0.498 approximation based on the natural semi-definite relaxation is kind of very natural. So the idea is that, you find someone who's basically done the work for you, and then you just like slap quantum all over the place and you get the result. But what we do is we use a hyperplane rounding generalization inspired by Jaap and his colleagues. And the idea is that really, what we want to do is with general max cut, you want to take each vector. So if we go back over here, for regular max cut, so I'm looking at the lower right, and for regular max cut, we have a vector for each edge. And then also by this reduction, or this equivalence for quantum max cut, we can think of getting a single vector for each edge. And so in the classical case, you want to take the single vector and take a single random hyperplane, a single random hyperplane, and sort of project this onto the normal of that hyperplane and take the sign to decide which side you live on. For the quantum version, we really need to get out, what we're trying to do here is to produce a product state. So, looking at the block vector of the state on each vertex, you need 3 parameters, and the sum of their squares should be 1. And so what you want to do is, instead of producing a plus or minus 1 from your vectors that the SDP gives you, you want to round a high dimensional unit vector to a 3-dimensional unit vector. And the algorithm that Jaap and company used was a little bit different, but it's kind of morally the same thing. So here, what we do classically, you just pick a single random vector and you use that to get your sign. In the quantum case, you pick 3 random vectors and use them to get the components of your block vector for your product state. And it turns out that the analysis is very similar to the max cut analysis. So in Jaap's paper, there's this nice hypergeometric function where when you kind of look at it, it's parametrized by sort of the rank of the vector you're trying to round to. And when you plug in 1 for the rank, you get the 0.878. And when you plug in 3, you get 0.498. So both of these algorithms, the exact same hypergeometric function is dictating their approximation behavior. So this is also why it seems really strange, this thing about like the first versus second level of the hierarchy. I mean, not only are you using the same relaxation, you're using very similar rounding algorithms, and you're using the same hypergeometric function for their analysis, yet in the quantum case, something different happens. So as we mentioned before, for quantum max cut, we really, you can boil everything down to having 1 vector per qubit. What happens when you're trying to approximate like positive 2 local Hamiltonian or general 2 CSPs? Well, now, you actually need, first of all, you're going to have a different constraint on each edge. So it's not just the singlet projector on each edge. And more generally, you're going to have to keep track of 15 Pauli moments, for each edge. And so this is why looking at more general 2 CSPs or quantum 2 CSPs is just nasty. It's nasty, not in a conceptual way, but in I can't really prove anything about this because I don't know how to evaluate, high dimensional Gaussian integrals kind of way, right? So, so this is sort of where we're stuck with all of that. But it's just more parameters to pass around. But there are a lot of analogies, and the same story kind of works. So okay, so let's see so in the last 10 minutes or so, I want to tell you about how the algorithms actually work and what they're using. So, the way to think about all this is that, so what really helped us in analyzing this is kind of moving away from quantum as much as we could to make things look classical. So the main idea was that instead of thinking about vectors for each vertex, now I'm looking at a higher level of Lasserre. So it's not, I don't just have 1 local terms, I have 2 local terms. So I have like vectors for vertices, but I also have vectors for like XX on each edge, YY on each edge, ZZ, XY, you name it. I've got vectors for all of those Pauli monomials. So the pic, what you do with all of these becomes complicated. At least initially, we had no clue how to start. But what ends up simplifying things is let's not worry about all of that, and let's worry only about what the SDP is earning on each edge. So as mentioned before, because you have a singlet projector on each edge, you can earn a value between 0 and 1 on each edge. And the SDP is giving us some relaxed notion of an energy you can earn on each edge. And so let's think about those energies and let's try to put constraints on them. And, you know, the first thing, so it turns out that to get any kind of decent approximation, you have to kind of, you have to overcome kind of cheating that can happen at a star. You know, so at a single qubit and all of its neighboring qubits, the first level SDP can actually cheat quite a bit. But you know, so for max cut, actually, there's no constraint, right? So if I'm looking at max cut, if I give you a single vertex, it's possible to cut all of the edges touching it. But in the quantum case, there's monogamy of entanglement. So I can't earn high energy on all of the edges touching a single qubit. And so I need to understand that somehow. And what helps is this, so Anshu, Gossett, and Morenz were actually the first to beat the 0.5 barrier for quantum max cut approximation. And they used an ansatz, you know, where they were using product states, but then also on pairs of vertices, they're putting down kind of singlets. So it's a combination of singlets and product states. So using that ansatz, you know, you can beat 0.5. And the thing you have to understand is what's happening on a star. And so there's this monogamy of entanglement bound by Lieb and Mathis that Anshu, Gossett, and Morenz employ and generalize a little bit. And what it basically says that if you have a star with Q leaves, the max energy you can earn is Q plus 1 over 2. So you know, this is saying like you're basically earning kind of what max cut could. You know, the most you could earn is sort of like what regular max cut could, because you know, regular max cut terms were sort of they have a maximum energy of half on each edge. So this is basically saying, you know, if you give me a big star, I can earn only a little more than half on each edge. And so this bound actually ends up being enough to get a good approximation. And our insight is basically that these kinds of bounds, you can actually prove them for the energies coming from these SDPs. You know, another way of saying this is that there's sum of squares proofs for these quantum monogamy of entanglement bounds. And so, you know, this is something we've been exploring more generally. But the basic idea is that, you know, if you look at the Lasserre hierarchy, if you go all the way up, it's going to tell you everything about a quantum state. But it's kind of a different picture than what we normally might use. And so any kind of monogamy of entanglement constraint should arise at some point in the hierarchy. And then it's a question of, you know, how do they arise and when do they arise? And so it turns out that the second level will actually get you the star bound. And so that was, you know, using that, we were able to basically generalize the Anshu, Gossett, and Morenz result to give like a generic SDP algorithm to get basically the same bound, you know, slight improvement, 0.533. But the way we got the optimal product state approximation, I think is kind of interesting. We actually needed to prove a new monogamy of entanglement bound that, as far as I know, you know, hasn't appeared in the literature before. And this is like on the triangle. So it's saying kind of what can you do with you know, energies on singlet projectors on a triangle. And if you look at the box on the lower right, the first inequality is what the star bound basically gives you. You know, this is a linear monogamy of entanglement constraint. And so this is sort of what was known before, but we prove a precise quadratic monogamy of entanglement constraint. So this lets us be more precise about, you know, if you have an edge with a certain value, then like neighboring edges have got to have bounds on how big they can be. And, you know, we actually think that these constraints actually characterize the energies that you can earn on a triangle. Not only do they hold, but they actually, you know, give you the feasible region. Yeah.
Sorry, can you help me? What are the terms in the upper left thing measuring? The traces? Are they, so the lowercase?
Yeah. So this is a trace of rho with each, you know, so the trace of rho with each projector of a singlet on an edge.
Right. So the H's are just terms of your overall Hamiltonian, right?
That's right.
Yeah. Thanks.
So yeah, right. So basically, you know, you'll see things like if you make one, you know, if you earn a 1, the maximum energy on one edge, so you're maximally entangled on these two qubits, then, you know, you can't do anything between these and these, and so you're only earning the traceless part, which is a quarter. You know, so those are the kinds of things you would see from these inequalities.
Okay, thanks.
So I mentioned the kind of ansatz we're employing. And before actually just showing you the high-level algorithm, there's this question of, why are product states interesting? Why should people even care about approximating quantum optimization problems with product states? It seems like, okay, maybe that was a great place to start, but shouldn't we move beyond this? And the answer is, in some sense, we can't. So, some really nice results by Brandau and Harrow show that, well, when you have regular interaction graphs and the degree kind of grows, that, product states will give you the optimum energy. Product states sort of converge to the optimum energy. And, as kind of like an application of this idea, not using the same techniques, but for example, we can pretty easily show using our kind of framework that if you just give me 3 regular unweighted graphs and I look at the best product state approximation, it's already better than the best thing we could prove, for the entangled version, using these matchings of singlets. And so, the point is that you've got to, if you want a worst case approximation, you have to deal with the regime where product states are giving you near optimal solutions or optimal solutions. And so I think that, any approximation algorithm is going to have some dependence on product states. It's going to be some algorithm that says, take the best of a product state and something else, or has to somehow otherwise account for product states. And so that's really the reason why it's very important to understand exactly how product states work and to do as good as you can on product states before moving on to other things. So
can I interrupt for a question about the Brandau-Harrow results?
Yep.
Is this some sort of random graph result that holds for typical graphs, or is this a worst case result that holds for every graph of a sufficient density?
So I've kind of conflated things. So the Brandau-Harrow is just for degree. So this is for like regular graphs and some generalizations of regular graphs for weighted things. But yeah, it's for an arbitrary regular graph of sufficiently high degree. So in other words, the energy kind of converges as a inverse polynomial in the degree.
Really? But can't you sort of put a very large clique somewhere that gives you large average density or degree, and then actually put your little instance somewhere in the corner here in such a way that that you have a graph with that satisfies large degree or density, and yet its solution is not at all a product state?
Yeah, we could talk about it more, but yeah, it's very surprising. But it's true. So the result is true, and so we could talk about why the kind of thing you're mentioning wouldn't work. And there's also a complementary result that says dense graphs, product states give you optimal energy or near optimal energy. So
I'm confused. You said high degree regular graphs. Those are dense, right? So the regular degree of each vertex is the same.
Right. So, but all I mean, the reason I distinguish between those is the, there's a precise relationship known between sort of the degree and the convergence to optimal. And so you could define, based on how close you want to be to optimal, you can define what you mean by dense. But yeah, those would be right. So when you're really converging to the optimal energy, sure, those are going to be dense too.
So I had a maybe a similar question as Ronald. So what's behind this really? Are there similar results for particular classes of sparse graphs? Is some kind of regularity or randomness behind this result?
So if you want some intuition on why this is happening, it's kind of related to this. Just think of the star, for example, right? So on this star, you're only earning, you can only, as a star gets large, you're only earning 1/2 more than 1/2 on each edge. And so, kind of 1/2 on each edge is sort of the upper bound for the product state energy. And so even just on a single star, you kind of see this behavior where, you can't really earn more quantumly, and it's really just monogamy of entanglement. It's really just, if you want to earn large energies on edges, that will drastically reduce what you can do on others. So that's really where it comes from. And by the way, this bound is tight. So on a star, you can actually achieve this energy, and it's even true for weighted stars. And it's very beautiful how it works. It's actually, it turns out that on a star, there's an optimal solution that's in kind of the single excitation subspace. So, it's just basis states with a single one. And then when you project down your Hamiltonian into that subspace, it just becomes a graph Laplacian. So the way you actually get the optimum energy on a weighted star is just look at the graph Laplacian on the star and look at the max eigenvalue. So it's really nice how everything kind of ties together. But that's where it's coming from, you know, that's sort of the idea. What Brandau and Harrow do is different. They generalize, you know, kind of classical decoupling results for SDPs and stuff, but this gives you some flavor of what's going on. So I think, you know, what should I do, Jaap? Should I speak a little more, or should I stop?
Well, you have some time left, so please continue. Yeah.
Okay. So I borrowed some slides here from Kevin, but I just, you know, I don't want to necessarily talk about too many details, but I do want to kind of give you some highlights. So there's a very generic algorithm. So it turns out once you look at the SDP, there's sort of a generic algorithm that's like the same basically for both the entangled rounding and the product state rounding. And the algorithm really is, you know, so we're getting these mu's on the edges, which is like what the SDP thinks you should be earning. And what you do is you find edges with large mu. So the point is that, you know, if I find an edge with large mu, then all the edges incident to it have to have small mu by that monogamy of entanglement bound on the star. And so then, you know, the idea is that you can kind of threshold. So you could say, you know, let me define some threshold and take all edges larger than that thresholded value, you know, that earn energy more than that threshold gamma, and they'll have some nice structure. So it turns out that you could prove that, you know, that you could relate sort of the threshold you pick to the degree of the graph you get on all the large edges. So you know, I can pick my threshold in such a way that the large edges will, for example, form a matching. So that's sort of the idea here. I'll go back to that slide, but you know, what we do for the rounding is you kind of pick your threshold. So all the large edges have to form a matching, or maybe, you know, for our other algorithm, we need them to form a degree at most 2 subgraph. But then you have, you know, you have all these edges that the SDP thinks you should be earning large value on. So on those edges, let's go ahead and put singlets down. And then, you know, worry about what's happening on the rest of the graph. And then it turns out that the algorithm is simply just take either the optimum product state, or not optimum, but take the product state rounding solution, you know, this 0.498 thing, or take the state where you put the singlet down on each edge in the matching and do nothing on the rest. And it turns out the better of those two will actually give you this 0.533 approximation. So it's, you know, once you go to this picture of just looking at edge energies, the algorithm is actually quite simple. But the analysis, you know, there's some interesting components. So for example, we need to argue that, you know, this matching that you get in this way, when you put singlets on those edges, you will actually earn a good amount of energy, you know, compared to what the SDP earns. So, you know, the SDP can only earn at most 1 on each edge. So of course, when I put a matching on each edge, I'm earning more than the SDP. But the problem is when I do this, I'm losing energy elsewhere. And so this is the reason why you have to worry about what's going on. But we relate this SDP to the matching polytope, which has been, you know, studied since Edmonds in '65. And so an exact characterization of sort of a linear programming characterization of the matchings in a graph is known. And that's the technique we use to prove that sort of, you know, you get a good solution. So that, you know, I hadn't seen too many quantum works where people are using kind of polyhedral results from discrete optimization. So this is exactly the kind of thing, you know, I want to see more of, is kind of synergies of you know, these kinds of areas. So so the difference in the product state algorithm is you also find kind of a matching, but instead of putting a singlet on the matching, you put some product state, you know, a specially designed product state on each edge of the matching. And that's what lets you get this optimal half approximation. So, you know, I think that's all I really want to say about the algorithm. And I'm happy to answer more questions. And the last thing I just want to say is that this work is part of the FAR-QC project that's funded by the Department of Energy. And, you know, we're looking at like optimization, simulation, and machine learning algorithms. And we're working with like, you know, groups from Maryland, Caltech, and others, and some of the other national labs. And you know, it's great having like working at the national labs. It is an academic environment, but funding models are different. And so, you know, it's really great having funding to do sort of academic style research. And so, you know, I just kind of want to make more people aware of this project. So, and in fact, some of you, we have QSoft, actually CWI and some of the QSoft institutions, when we initially proposed the project, we're supposed to be partner institutions, and then the pandemic hit, and no one could travel and we couldn't really collaborate. So I'm really glad to be interacting with you all, because I would love to kind of explore some more collaborations. So that's it for me.